In this video, we'll do an example of a calculation of the non-Coulomb electric field in the case of a time-varying magnetic field. What I have here is a magnetic field that points up and it changes as a function of time. What I want to find is, let's say, the magnitude or the electric field, the non-Coulomb electric field that is created at this area due to the changing magnetic field. I do want to, before I start, I do want to point out something important. You can, anytime you have a changing magnetic field, you will have the presence of the non-Coulomb electric field. Always. In space, around that, the area where the magnetic field is changing. So if this is the only part of space where the magnetic field exists and is changing, your non-Coulomb electric field will be present here, but it will also be present outside of that area. Okay, the non-Coulomb electric field is not confined to the space where you have that magnetic field. It will exist everywhere around it. Now, one more thing. The non-Coulomb electric field will exist in the space here independently of whether you have something there to detect its presence or not. And what I mean with that, we have seen that if you have a loop here and you have a bulb in connected in series with that wire, with that loop, then the non-Coulomb electric field will drive a current in the bulb and you will see the light. Now, you don't have to do that. The non-Coulomb electric field will be present there even if there is no bulb and even if there is no loop at that point to detect it. All right, now, and in this problem, actually, I don't have a loop. I don't have a loop with a bulb. I don't have a loop with an ammeter attached to it to see what the current is. The only thing that you physically have is a changing magnetic field. That's it. And our task is now to find the non-Coulomb electric field that exists here. Now, I will draw, if you want, a loop that will allow me to do the path integration of the left side of Faraday's law. Okay, this is not an actual wire. This is just a loop I'm using to do the integration. Now, let's say that I'm choosing my area dA here, and I'm choosing the dA vector to point up, which means I need to do the integration. Okay, this will be the dl. It will be around the loop this way. At this point, it's going to be going away from us. So dl will go into the page, whereas if you look at it at this point, the dl is going out of the page. Okay, now I am consistent with applying, this is how I apply the right-hand rule on Faraday's law. The way that I do the integration, the path integral is consistent with what I will use for dA on the integral, the area integral for the flux. Now, moving on, I can do this B that changes as a function of time dot dA. Let's say that my loop, let's do my loop has this radius. Let's call that, let's say that this is S, the radius. So now here I will write the vector dA as S d phi ds, and it does point in the z hat direction, I have made the choice here to use the cylindrical coordinate system. So the dA vector points in the positive z direction, and it is sdf ds. Now my magnetic field also points in the z hat direction, and this means that the dot product is the strength of the magnetic field times S d phi ds. Now I could have also, instead of using the strength, I could have just done the z component of the magnetic field, since it points in the z direction. So I could have also written bz as a function of time. And then I have to do, this will allow me to do the surface integral. Now let's do the variable of integration. I'm gonna make that to be s prime. S prime will go from 0 to s, and phi will go from 0 to 2 pi. I'm not sure at the end of the day which one is going to be more useful, bz or the magnitude. For now I'm going to go with bz. And then I have s prime d phi ds prime, and I will move on here. This will give me a magnetic flux that is bz as a function of time. One thing to keep in mind for this example, the magnetic field is uniform in the area of this loop, but it changes with time. As far as the integration is concerned, this is a surface integral, and since the magnetic field is uniform in that surface, I can take it out of the integral, and then what we will get from here is the pi s squared for the integral of s prime ds prime, and the integral over d phi will give us the 2 pi. Now this is the magnetic flux, and the right side, let's say this is equation 1, let's call this equation 2. Using the right side of equation 1 and what I found for equation 2, since I found the flux to be this will be minus pi s squared d bz, which is a function of time, over dt. Now for the left side of equation 1, I know that the non-Coulomb electric field will point in the phi hat direction. So to find, this is what I need to calculate around my loop, the non-Coulomb electric field dot dl. That's the closed path integral. I will write the non-Coulomb electric field as E comma phi for the phi hat component times phi hat. I know that the non-Coulomb electric field does not have a z hat component or an s hat component, And because I'm doing the integration around that circular loop and I am going in the positive phi hat direction, I will write dl as s d phi hat, and this will give me the dot product between those two vectors to be just the phi component of the non-Coulomb electric field times s d phi, which I can use here. This is the integral when phi goes from 0 to 2 pi. The phi component of the non-Coulomb electric field times s d phi, and this will give us 2 pi s times the phi component of the non-Coulomb electric field. Let's call this equation 3. And then if we combine equations 1, 2, and 3, no, not 2. Actually, let's do let's call this equation 4 then. So it will be 1, 3, and 4. We get that the non-Coulomb, the phi component of the non-Coulomb electric field is equal to minus pi s squared divided by 2 pi s, and then the time derivative of the z component of the magnetic field. And of course we can cancel out the pi with the pi and the s with the square, and this will give us minus s over 2 . Now this is the phi component. If you want to express, if you want to write the non-Coulomb electric field as a vector, just multiply this with phi hat, because that's the phi component, and you will get the non-Coulomb electric field.